Hello, my name is Abdulrahman Mohammed, and I will present the section of the tutorial focusing on speech representation learning paradigms. First, what makes speech representation learning unique? Like, what are the problems that we need to overcome when we are learning speech representations? First, speech inputs have variable number of lexical units per sequence, and these units themselves, they have variable length, and they do not have segment boundaries in the raw audio. Add to that we do not, like, as opposed to text and language representation approaches, we do not have a predefined dictionary of units. Like in the case of text, we have characters, words, or subword units that we can rely on when we are learning language representations. Here we do not have that predefined dictionary of units. And add to this that some of the speech tasks would require orthogonal information to be maintained in the pre-trained model. So some downstream tasks like speech recognition would require the representation to focus on the content of the signal rather than the style, while speaker ID or diarization would require that the model focus more on the content, on the style, while being invariant to the content. So to have a representation learning approach that would reach state of the art on at the same time on multiple different downstream tasks would require kind of taking care of this all these considerations. There are many speech representation methods that got developed over the past few years. In this tutorial, we'll kind of categorize them into three broad categories: contrastive, predictive, and generative. And to clarify terminology here, generative, I'm referring mostly to reconstructive approaches as opposed to generative models that contain latents that you can sample from for generating novel samples. But this is not what I'm going to talk about. It's pretty much reconstructive approaches of representation learning. First, let's focus on constructive approaches. Starting with contrastive approaches, starting with contrastive predictive coding. So CPC is the first successful representation learning approach for speech recognition. It triggered a lot of research in speech and visual representation learning. The main pretext, the pretext task, or like, the main idea here that drives learning is how to distinguish correct or positive samples from negative samples. And the question is, okay, how can I decide, or like, how should I decide which samples to be positive and which samples should be negative? So first, let's look at the architecture itself. So you have the audio input. You have time, like, you have a feature vector every time step. You run it through an encoder that produces the latent representation Z. So these Z vectors are pretty local representation of speech. And then, given this local representation Z, you have the aggregator network that aggregates them to produce a contextual representation CT. The pretext task for CPC is to bring the contextual representation CT and nearby frames at T+1, bring them closer together while pushing away representations that are farther away in the signal or sampled randomly from the mini batch. The scoring function F here is just the log bilinear relationship between the ZT plus K and the CT, where K here is just the distance. So in the case the distance 1, you wanted to bring closer together the context vector CT and the input representations ZT plus 1. Notice that we have different W's for different K, for different distance K. So, for example, in this picture, we can have multiple different positives that are, all of them are in close proximity to the CT at time t here. So this is the kind of like the idea of the info NCE loss, is that We have the numerator with positive samples containing the score of CT at time step, the CT and the other kind of like, Z feature vectors at multiple Ks, where K could be running between 1 to 10, for example, in kind of like focusing, like designating positive as feature vectors of close proximity to the current time step, while the denominator contains negatives that are sampled randomly from the mini batch or from further away time steps in the signal. So the distance between xj and ct. Xj, of course, is represented by the zj, the output of the encoder at that time step. The CPC paper shows that the M4NCE loss maximizes the mutual information between the input signal and the learned latent representation, C. And now how you are sampling the negatives would determine the nature of these representations, which is, I believe, like it's a kind of fascinating thing in the whole, business of like self-supervised approaches, like how you are playing with loss function and negatives and positive will determine the nature of this representation. So in this case, if you select your negatives to be sampled from the same utterance, you will pretty much focus on the content and discard the style, because the positives and negatives would come from the same speaker, assuming that it's the same speaker in a single utterance. While if you select negatives from other samples in the mini batch, you would focus on learning representation that distinguishes speakers and not necessarily focus on the content, because again, assuming that multiple speakers will be at different speakers will be in different sentences. So if you bought CT and ZT plus 1 from the same speaker, and the negative Z that you want to kind of maximize the distance between it and CT coming from a different speaker, coming from a different sample, the model, the easiest kind of feature for the model to capture would be that the negative is coming from a different speaker, since so this could be helpful for applications like speaker ID rather than ASR. And this actually what also was found by the authors in the paper, is that for the best performance on phoneme classification, sampling negatives from the same utterance provided them with the best performance. The success of the CPC approach inspired a lot of follow-up work, either to produce better architectures or different normalization approaches for stable training. Of course, these approaches require long training to learn good representation. So having a stable recipe is the kind of a key to reach these high quality representations. Another extension kind of added another direction for the aggregator network. So the picture I just saw going from left to right, that aggregates the information from left to right. An extension had another aggregator network that's going from right to left, and the loss function would combine this information from these two directions to learn the representation. So again, remember that this bidirectional and CPC was done in a pre-BERT days. So in this case, having this bidirectional was the kind of the main idea to aggregate the full context to learn this contextual representation. Other approaches investigated multilingual transfer of representation. They actually found it successful for multilingual transfer in these papers, and many more extensions that was developed for CPC. The second approach I wanted to talk about is Wave2Vec 2.0, because it is the first approach to show significant improvement for low and ultra low resource ASR. It produced impressive results on multilingual representations, and it has a very strong performance on a wide range of downstream speech tasks. So first, let's again look at the model. Start with a waveform, run a CNN encoder, and this CNN encoder will produce latent representations Z or you can call it here the input representation, because later on we'll run it through the transformer network, and we will mask spans of input at random positions, highlighted here by the gray boxes M. And these bands would run about, like, say, 200 milliseconds. So it's not short ones, but really long spans of audio that kind of be an average length of a phoneme or something, or even a little bit larger. And then only for masked positions, you would take the output of the CNN encoder, the input features, and you run it through an online quantization algorithm to get you the index that you will embed it in some embedding table to get a representation Q. So the input at masked positions would be quantized and embedded to get you a vector Q. Now, the masked input, you run it through a transformer network, a deep transformer network, to produce the contextual representation C at the masked positions. And the whole philosophy of the model is to maximize the similarity between the learned contextual representation given the partial view, or like given the masked view, C, and the quantized input features at the same position. So in a way, let me mention the loss function here. So the loss function is the same as the InfoNCE. In a way, it's similar to the InfoNCE, the CBC idea, but how we are sampling positives and negatives are different, and the transformer network is much more powerful in learning this contextual representation C. So the same InfoNCE loss, the similarity metric, the similarity function here is just a cosine similarity between the contextual representation C and input representation Q. So again, Q is just the input representations to the transformer, but quantized and embedded vectors. The denominator here contains the positive sample plus k other negative samples that are chosen from the same utterance from other masked positions. In this picture, they are the other green boxes on the right. So in the case of Q1 and C1, they will be appearing these are the positive bare, and then we have a bunch of negatives that we sample from other masked positions in the same utterance. The online quantization algorithm that was used in Wave2Vec is the Gumbel Softmax. You can see here the PyTorch implementation of the Gumbel Softmax. As usual, I would if you know the Gumbel Softmax algorithm, you add the Gumbel noise and you have a temperature that plays with how you are sampling these units. For example, you start with certain temperature at the beginning that allow you to have lots of to navigate more in the space of discrete units, while close to the end you kind of anneal it to kind of stop the exploration a little bit and have more stable codebook. The approximation that was used for the backward is a straight through estimator, as shown here in this example code. Couple implementation details for Wave2Vec 2.0 is that, one, the quantization here is not just a single code book, but rather product quantization was used where the same, like for the same input position at step 1, for example, rather than just embedding it into a single code book to get Q1, it was actually embedded into multiple code books. So this way it has a better kind of coverage of the space, because product quantization was shown to be much more effective in higher dimensional spaces. And you get these multiple code books, you will have multiple indices, you will embed them into different tables, embedding tables, and you will concatenate the representations as your Q vector. Another detail here is that given the importance of these discrete representations, because they are actually important, because they are influencing the positives, both positives and negative samples in the algorithm, an entropy loss, or like an entropy, like kind of, you want to maximize the entropy of that softmax, of the Gumbel softmax, such that you ensure that you have a diverse codebook, because otherwise you don't want that codebook to collapse, and or like, you know, you have very few indices that are active. For example, you can imagine a case for collapsing, it would be like, you know, speech and silence only that are being used. But you want to ensure that this codebook is diverse enough, it's being used across multiple time steps in the same utterance and many time steps in the whole many batch. Hence this kind of entropy maximization term in the loss function. One other detail relates to the negative examples here is that, as I mentioned before, they are sampled from masked segments in the same utterance, but more importantly, for positions that does not belong to the same code word, i.e., if Q1 here, for example, belong to the index 17, you do not want to sample other negatives from the same utterance that belong to the same code word 17. You would discard this one, such that like you do not want to confuse the loss function by having negatives that are actually not negatives. They are should be actually positives. So yeah, this is a kind of like couple considerations to ensure like stable training and high quality representations, given the empirical results in the paper. For the results, Wave2Vec 2.0 was the first approach to get into like a single digit word array in LibreSpeech test other using only 10 minutes of labels. And as you can see here, if you pre-train it in 60,000 hours of audio with a transformer LM, you really can reach that level of performance. Another interesting thing about Wave2Vec 2 was that it was the first algorithm, self-supervised algorithm, to produce competitive result compared to semi-supervised learning approaches like Know the Student, as you see in this table. And of course, given the success of the approach, it inspired a lot of follow-up work, either for multilingual extensions, more effective quantization methods, combining contrastive and predictive losses for learning even better representations, etc., and many more extensions that was proposed in the years after 2020. The second family of approaches I'm going to talk about are predictive approaches, starting with Hubert or hidden unit BERT approach. The key idea for Hubert was that it should be a simple method just to apply BERT style representation learning for speech, because we know that we do not have dictionary in speech given the continuous nature of the input, and we do not know the segmentation of it, so we cannot directly apply BERT. And the Hubert was just like simple, try a very simple trick to get it to work. And to our surprise, it matched or improved upon the state-of-the-art performance on ASR and getting a very good performance on it, sometimes even the top performance on many speech tasks. And the high-quality discrete units of Hubert facilitated a lot of follow-up work on textless NLP, where you can use discrete units to do generation of audio and generation of dialogues, as will be highlighted later in the tutorial. Let us start with the model here. So you start with a waveform at the input. You run this signal processing approach just to get MFCC or log-mill filter bank, and then you do offline k-means quantization. So once you do that for every input, you actually have frame labels at every 10 millisecond or 20 millisecond, depending on what's the kind of frame rate of your of the signal processing that you did to extract the MFCC or log-mill filter bank. But now you have the frame level labels of your input. So you do not need the quantizer anymore, you just have these labels. Then you run your input through the CNN encoder, you do again the span masking, And then you run it through a transformer network to get contextual representation. And then you need to predict the target labels or k-means labels for the masked positions. This is conceptually similar to BERT, but it's done on these hidden units that we discovered from the k-means algorithm. The main kind of motivation or philosophy of this model, or what makes this model work, is that it does not focus on the quality of these labels. So these labels are imperfect, they are bad, because k-means is not necessarily perfect, learned from MFCCs. But although it is bad labels, they are consistent in being bad. So, and this consistency is much more important, because even if the model kind of confuses ka and ga, it doesn't make a big difference, given that we are looking at ka and ga in context of what other units that are appearing on the sequence. So using the masked prediction loss, the Hubert model is driving the learning of representation. So simply, for the masked positions, you need to maximize the probability of the k-means label of that position. And the reason that this works is that the transformer network here acts as a combination of an acoustic model and the language model, because it need to learn some latent representation of the unmasked segments Z, and then temporally combine or like kind of learn what would connect, what would relate positions that are masked but with positions that are unmasked, such that it will learn the prediction to predict the true label at the masked step. So having this masked prediction loss is a key in getting this algorithm to work. So in the paper, it was shown that if you try to predict every single output, given the audio input, you just try to predict every frame label as if it's just a frame level loss function in a supervised SR. If you treat these k-means label as actually gold standard labels, and you try to predict all of them, you do not learn good representations, because now the model just learns an acoustic model, how to map the input to some output label. Using the masking prediction loss is the key idea, is that it forces the model not to just listen to the input, but listen to the input and relate what's happening at different time steps, such that it will predict the output. So in a way, the language modeling is kicking in the transformer component to learn these high quality representations. Now, once we learn good representations of Hubert, there is nothing preventing us from taking these Hubert features from a previous iteration, run offline k-means again to get even higher quality target labels and play the same game again. Run the audio, do masking, and predict the masked time steps. A couple implementation details that actually was important to get this algorithm to provide state-of-the-art results. One is initially to use small code book sizes like 50 or 100, because we needed to focus on broad phonetic categories rather than getting to the nitty-gritty differences between within the speakers. Like, for example, if the sound produced by, say, 400 speakers, you could have multiple subclusters of the sound if you have, let's say, a code book of 7,000 or 20,000. So this kind of having the limited capacity of the codebook size prevented falling into this problem and forced the model to use its budget wisely to focus on the broad phonetic categories. The other observation that helped this model to perform well in the subsequent iterations is that not like when you're running the second iteration of Hubert to take the features not from the top layer but somewhere in the middle layers. What was found consistently to work very well for multiple data sets is to use in the first iteration to take layer 6 representation just in the middle of the network, and then you kind of take the layer 9, which is the kind of like the upper quarter of the network to run the k-means algorithm. So empirically, this was the best performing layers across many different speech tasks and datasets. On average, like at the end of the day, some of them will be slightly similar to like layer 11 or like layer 7, etc. But at the end of the day, as a good rule of thumb that was found to work very effectively was to use layer 6 and layer 9 of the base architecture to do the subsequent iterations of Hubert to get good representations. And this is actually what we found is for ASR, the representations of Hubert was able to get better performance than Web2Vec on say like 10 minutes and slightly better on 1 hour. Of course, they are getting closer together as you have many more hours of supervision. The other thing is that it produces best representations for multiple downstream tasks on the super benchmark, as we will discuss later. Of course, this was at the time of the publication. There are many other extensions of Hubert that came after. So again, like CPC and Web2Vec, Hubert inspired many other follow-up work. One of them combined mask prediction with denoising pre-training, like the WaveLM, which actually produced even better representation than Hubert in the super benchmark. Like random clustering as another kind of bold move, like rather than using k-means, which is pretty cheap, what about just using random codebook with some constraint on the distribution of the code words, and pretty much it was as effective in learning representation as k-means algorithm. And the audiovisual Hubert, which extended Hubert approach to audiovisual speech recognition when you have lib information as well as the audio signal to produce high quality representation that can work for noisy speech recognition and for lib reading scenarios. Another like line of research that was enabled by discovering high quality representations is textless NLP, where you can model the input, the audio input with every aspect of the audio, as like laughter, any audio event that's happening within the discussion or interruptions, etc., such that this will have richer representation of the input, and it will allow us to deal with the speech task as any other NLP task, because you have the discrete units that can act as pseudo language for speech generation or dialogue generation, as will be highlighted also in later parts of this tutorial. The second predictive approach I'm going to talk about is Data2Vec. It is the first algorithm that was shown empirically to work to achieve state-of-the-art or near state-of-the-art for all the, like for speech and vision and text inputs. The core idea of Data2Vec is the following, is that, again, it revolves around where can I get the targets. So if you have a masked input, you run it through a transformer network, you have your latent representations. Where can I get high quality targets for these masked positions? The core kind of idea in this approach is, what about using the same transformer model to predict the outputs of this masked position, but using unmasked input? So in a way, you have a teacher mode and the student mode. Let's assume that now they are the same model or the same weights. One of them, you run the input in an unmasked fashion, like, the unmasked input, you run it through the teacher model, and to record a bunch of targets. And then when you run the masked version of the input, you use what the teacher model produced as the target of the outputs of the student model. But now, the student and teacher model, because they are assuming here that they are the same copy of each other, How can you avoid that the representation will collapse, that the student model will just conspire to just make constant output for all the masked data? And just like if they are constant, they can just predict this constant, and your loss will just get to zero very quickly and learn some trivial representations. The answer or the solution to this problem is that rather than using a teacher model that is a copy of the student, what about using a teacher model that is just slightly older copy of the student? And to do this in a kind of like streamlined way, you can use an exponential moving average of the student model. Once you do this exponential moving average using the momentum parameter that control this moving average, you can determine how close or farther away the teacher model from the student model. So this way you can control the representational collapse that could happen. So as we see in this slide, in the lower in the second equation here, this shows the momentum term tau that controls the distance between the student model theta and the teacher model delta. Also, you take the targets yt from the teacher model that takes the unmasked input and use it as targets of the contextual representations produced by the student model. The L2, the smooth L2, the smooth L1 loss is being used here. So within the using the hyperparameter beta, within the kind of like smaller differences between the targets and the predictions, you apply the L2 loss. Otherwise, you apply the L1 loss. But there are a couple implementation details here to ensure stability of learning. One, you need to carefully tune the momentum factor tau. Otherwise, if the teacher model is tracking so closely that the student model, again, you will have this collapse in learning. You need to control how far at the beginning of learning versus the end of learning, how far you are, the teacher and student model are tracking each other. The other one is you do not want to use high learning rates to train your model, because again, you don't want the student model to be changing so fast. Otherwise, again, it will collapse. And also you need to use long learning rate. You need to avoid short learning rate warm-up. So you need to use long learning rate warm-up, again, to ensure that the representation will not collapse, that the student and teacher will just conspire together to learn some trivial representations. Another important detail for getting the high quality representations reported in the paper is to use the YT is not just from a single layer of the teacher model, but actually to be average over multiple latent representations of multiple layers. Here they are using the top K blocks of the teacher network. But to avoid that some layers will overwhelm the average, you do instance normalization of the outputs of each layer first before averaging them. So also you can kind of get rid of some global information that is contained in the sequence that is not necessarily related to the content. So once you get rid of it, this will ensure that you have better representations that are focused on quality in the content, higher quality representations focused on content. You average them together and use them from the top K blocks and use them as the targets of the student model for its contextual representations. So given this, like as I was describing this for speech, but you can imagine it's a very abstract approach that you can apply for speech or visual input or textual input. And the kind of philosophy of the model here is that you need the student model to be able to predict the complete contextual representation from incomplete inputs. So again, so this kind of idea of just predicting the full contextual representation from incomplete one is the reason that this approach is producing high quality representation that produces the current best results in representation compared to Hubert and Wave2Vec 2.0 and WaveLM, as we see in this table, even when we use 4-gram LM. The last category of approaches I want to talk about are generative approaches, again, reconstructive approaches in nature, starting with the vector quantized variational autoencoder, VQVE. It is a generative model with discrete latent variables, and I'm talking about it because it influenced a lot of subsequent research work. It was developed, was presented in 2017, and since then, it has been so influential in many other approaches that got developed. The core idea here is that you represent the input, you kind of like using an encoder network, and then you look for the nearest embedding vector E. If you have an embedding table, you look at the nearest embedding vector E to the encoder representations, and that embedding vector E, of course, it kind of relates to an index I or K here, and that embedding vector will be the input to the decoder to reconstruct the input again. So it's a normal autoencoder, but with this funny quantization in the middle that enforces the model to learn some categorical latents. The loss function is kind of like contain these three terms. One term is the reconstruction term, that you need to be able to reconstruct the input again through this latent representation, of course, embedded in the embedding table. And because the straight-through estimator is used, you don't have gradient for the embedding table, so you use vector quantization to train this, and this is the second term. And to ensure that the embedding table and the encoder representations are staying within the same numerical range, you have this commitment term, the third term in the loss function. Here, the SG is like a stop gradient operator, so that you have stable learning, that you are updating the different components of the model independently. So this is one approach for generative approaches. The second one is autoregressive predictive coding, which also another approach that influenced a lot of subsequent approaches. It is inspired by the next step prediction loss for language model training. So speech is a sequential task, or sequential in nature, sequential process. So if you have input at time step t, you can predict t plus 1. But given that speech is smooth, you do not want to predict just the next time step. This algorithm is trying to predict the frames in steps in the future to force the model to learn something about the structure of the speech signal. And it was found that it helps in content-related tasks and style-related tasks. And it inspired a lot of follow-up work in generative approaches. Another family of approaches that was developed within the generative paradigm is masked reconstruction. In the masked reconstruction, it's inspired by the success of BERT approach in language. And the proposal here is to reconstruct the continuous input from a masked view of the same input. So there were multiple papers that appear kind of concurrently, focusing on the same idea of masked reconstruction, and how this is kind of like different from other techniques like Hubert, for example, is that Hubert's trying to predict the discrete labels from the k-means, kind of building the language modeling into the explicitly more into the model, while these approaches are reconstructing the continuous input as is, forcing them to entangle information about the content and style, because if you need to produce the input as is, you need still to retain information about the speaker or the style of the input. The Thera approach here is not just doing the masking over time, but also over frequency, and all of these produce again, like very very competitive representations, both for content related tasks and style related tasks, as been presented in the benchmarking section. And this concludes presentation of my section about the speech representation paradigms.